There's this story that every data science course tells. It goes like this. A man storms into a Target outside Minneapolis, coupons in hand, and demands to speak to the manager. His teenage daughter has been getting mailers for cribs and baby clothes. She's still a teenager. She hasn't even graduated high school. Why are you sending her this? The manager apologizes, says he'll look into it. A few days later, the father calls back, but this time it's to apologize rather than seek an apology. It turns out his daughter really was pregnant, and Target knew before he did. Now, it's not as though there's an is_pregnant column in some database somewhere. How did this happen? It's kind of a perfect story, and a statistician named Andrew Pohl did some analysis and was able to build his own pregnancy prediction score based on Target data by looking at just 25 products. He could use those 25 to estimate the due date of the pregnancy. But that isn't a miracle, it's just data. Purchasing a pregnancy test is a decent predictor of having a baby 8 to 9 months in the future. Buying gender reveal party invitations probably indicates you're going to have a baby in 1 to 3 months, I would guess. But what do I know? Andrew Pohl had the data. He found things like supplements are often bought early in a pregnancy. Items like unscented lotions start showing up on the receipts in about the second trimester. So there's this emotional hook that Target knew before the father knew. And depending on your definition of knew, of course it did. In fact, it wouldn't surprise me to find out that the father is almost always the last to find out about a teenage pregnancy. A spreadsheet beating him to it is not a sign of an advanced machine making a startling prediction. It's a machine that can find a probabilistic needle in a haystack of data. The Target story is really a story about inference, a machine noticing a pattern that you did not know you were giving off, and it gets more unsettling as the signals get more intimate. Here's Santiago de Leon, a PhD student at the Kaplan Institute in Bratislava. He studies what your eyes give away as you browse.
We don't kind of consciously control our eyes. When we get to the point where people are like eye tracked constantly, you can start to figure things out about them that they're not even like that conscious about either. And it reveals so much information about you, like semi-consciously or even consciously, that you may not even know about, that it can be pretty crazy. There's other things as well, like with eye tracking data, some people are working on trying to diagnose Alzheimer's, all these different things. So like based on your eye tracking data from Netflix, if it were to get released or something, someone can try to diagnose you with that, with some sort of mental illness or something like that, right? And I don't think people are happy with that.
So at every level, we're emitting data, and the right system that can capture that data and analyze it might find a pattern. This begins the finale of the Data Skeptic season on recommender systems. The season we've talked to a variety of researchers about what recommendation really is and what it isn't. I want to thank Chicago's Run and Punch for use of their song, We've Never Met. Check it out on Spotify. So this is the first of a 3-part finale of Data Skeptic recommender systems. This part is more of the origin story, where recommenders come from, and how you even measure whether one is even any good, right after this message from today's sponsor. I travel quite a bit, and one thing I've learned is that the internet doesn't always work the way you expect. Sometimes I'll go to a website or try to access something I'm used to using, only to get a message like, "This content isn't available in your region." Or I'll find myself working from a hotel or airport Wi-Fi, wondering who else is on that network and what can they see. That's one reason why I started using Proton VPN. Proton VPN keeps what you do online private, and lets you use the internet the way it should work, open, secure, and on your terms. Whether I'm traveling, working from a coffee shop, or just browsing at home, it gives me a little more confidence that my browsing activity isn't up for grabs. What I also appreciate is that Proton isn't just another VPN. It's backed by strong European privacy laws. It has a strict no-logs policy that's been independently verified, and it's open source, so anyone can go and inspect how it works. Plus, with servers in more than 145 countries, fast connections, and built-in ad and tracker blocking, it just works without getting in the way. It's easy to get started. Right now, Proton VPN is offering our listeners 70% off a 2-year plan when you go to protonvpn.com/dataskeptic. Let's spell it out. That's protonvpn.com/dataskeptic for 70% off your 2-year plan. That's protonvpn.com/dataskeptic. So what even is a recommender system? It's a label for many different types of systems built many different types of ways. The long and short of it is to suggest the right item to the right person at the right time. That's more or less how the field has framed it for decades. And then in 2003, Amazon publishes the paper that drags all of this to the web scale. Item-to-item collaborative filtering. It's not find users like you, which is expensive when you have tens of millions of users, but find items like the items you already touched. It's the engine behind customers who bought this also bought, and it is quietly one of the most commercially consequential algorithms ever shipped. Strip away the history and the plumbing, and my co-host from Data Skeptic Graphs and Networks, Asaf Shapiro, frames the whole idea in a single line. A recommendation is just a link prediction.
You connect things that aren't connected, right? What are the edges there? I like to categorize it to two parts, like explicit connections, edges, and implicit. So when I look at explicit, I look at edges that there's no argue that that's a network. When we talk, right, we are creating a network. What defines these edges? Like physicists would say, we exchange information. Information is an edge, or maybe a dependency could be an edge, and so on. Things that are absolutely dependent on each other. On the other side of the spectrum, there's the implicit connections or edges. That's where recommendation systems kick in, because I like let's say Marvel movies. Okay, I like Spider-Man and I like Ant-Man. I can assume that I would also like Captain America, although I haven't seen it. So it's what we call a recommendation or a link prediction.
Underneath all of it, there are really only 3 philosophies, well, 4, but let's start with 3 for recommending anything. And they are the DNA of everything else in this series. First is content-based. Recommend things that resemble what you already liked, and judge those things by the features of the items themselves. What is this book about? Second, collaborative. Ignore the items entirely, forget about their features, and lean on the crowd. Recommend what people like you liked. And the often forgotten stepchild or cousin, knowledge-based recommenders. The best example I can think of is an old restaurant recommender. You point at a place that you already love, and you say, like this, but in LA when I go on my visit, or like this but cheaper, or nicer, or this type of cuisine but closer to my house. A knowledge-based recommender can then look at just your request and what the system knows about the restaurants and the food. And then lastly, fourth, the option most recently coming to the table, large language model-based recommenders. And I'll put agentic recommenders in here as well. Those that leverage the profound breakthrough of large language models and let next token prediction take care of it, if it can. But I'm getting ahead of myself in the history lesson. Let's take it now to 2006 for the contest that made recommender systems famous. Netflix did something a little wild. They dumped 100 million real movie ratings onto the internet, and they said, if you can beat our recommender by 10%, we'll hand you $1 million. They called it the Netflix Prize. Netflix had a system called Cinematch that guessed how many stars you would give a movie. Under the hood, it was a fairly ordinary collaborative filtering system from what I've been able to discover. For every pair of movies, it measures how similar people tended to rate each of them, in the cases where they did. And then it uses that to predict your rating for something you haven't seen yet, leaning on your previous ratings of films that are most like it. Simple, carefully tuned, and stubbornly hard to beat, apparently, at least initially. Entrants just had to predict those ratings, but better than Cinematch. The early frontrunners leaned on plain old collaborative filtering, or maybe adding their own little spice to it somehow. But the idea that took the big leap forward didn't win the prize, but the first big leap, matrix factorization. Now, if you're unfamiliar with the technique, I'll try and give you the intuition without the math. Instead of comparing you to your neighbors, You describe every movie and every viewer as a short list of numbers, a vector, a handful of hidden dials, what today we might call an embedding. Think of every number in that vector as a dial. Maybe one dial ends up tracking how much action a movie has. Another dial tracks something like the quirkiness of the film. And yet some third dial might measure some flavor no human being ever bothered to name. You place a movie on those dials, you place yourself on the same dials, and a good recommendation is just a movie whose settings line up with yours. The clever part is where the dial settings come from, because nobody actually sets them. It's an unsupervised technique. The algorithm starts from random numbers, sees only the ratings people already gave, and nudges every dial until it finds some n-dimensional space within which to embed that data. But mechanically, you just factor one enormous, mostly empty matrix of user by movie ratings. You factor it into two small tables, one row per person and one per film. Then you multiply those back together to fill in the blanks. Nobody designs the dials, they fall out of the math. And the person who cracked this one open wasn't from a lab or a company, it was just a guy blogging under the name Simon Funk. Sitting near the top of the leaderboard, he just posted how he did it, wrote up his whole approach and gave it away for free, and overnight, half the field was running his method. From there, it became an arms race of piling models on top of models. The winning entry from a team called Belcore's Pragmatic Chaos wasn't one clever trick. It was a Frankenstein monster of over 100 of them stitched together. And the finish was actually quite ridiculous. There's some good drama here. Remember that the whole thing was scored on root mean square error. Netflix's own Cinematch was around 0.95, so to win the $1 million, you had to get about 0.85. And in the final stretch, two teams both got there, and to 3 decimal places their results tied. Effectively a photo finish. Neither was really better than the other, but the rule of the game was that ties go to whoever submitted first, and Belcore's Pragmatic Chaos had turned theirs in about 20 minutes before the other team. A 3-year $1 million contest, and the last 20 minutes decided it. Why isn't there a Hollywood movie? Perhaps the main win of all this was real media attention. Outfits like the New York Times and Forbes all covered it, although the story they told has a twist, because Netflix never actually shipped the winning algorithm. It's hard to say if they made the right call or not, but whatever decision makers there were said it was too tangled or too expensive to put in production. So the grand prize solution, 3 years in the making, basically went in a drawer. But the prize got a lot of spotlight, and the other thing it did was drag a spotlight onto every weakness of collaborative filtering. What do you do with a brand new user who's rated nothing? That's the cold start problem. What about the fact that almost everyone has touched almost nothing in the catalog? Even a dedicated movie rater has finite time and rates finitely many movies, maybe a single-digit percentage of the whole catalog. And what about popularity bias, where the well-advertised blockbusters just drown out everything smaller? Or what about people stuffing the system with fake ratings to game it? Recommender systems are trickier than they let on at first glance. So the Netflix prize had its own trap in terms of how it measured. The prize graded you on rating prediction. Just guess my star rating. Get scored on how far off you are. Remember, this is root mean squared error, or RMSE, but forget the acronym. All it really does is measure an average. How far your predicted stars landed from the real ones. It's like judging a matchmaker on how well they can guess how much you liked your exes. It's a well-intentioned metric, but one trying to solve the problem adjacent to what a recommender system is really supposed to do. You didn't come to a matchmaker to relive old relationships. You came for the next date. Guessing how you'd rate a movie you've already seen is a different skill from putting a great one in front of you that you've never heard of. And as the field has progressed, the approaches have evolved in many different directions, but most notably, to try and measure the list returned. Most recommenders hand you a short ranked list. Top 10 songs, top 5 products. And yes, if you've sat through a machine learning class, precision and recall apply here. But let me describe them for you without a single formula. Here we are at a dinner party. You've been invited. Mostly strangers, the host is going to introduce you around. Now, precision is this. Of the handful of people that he puts in front of you, how many were a good match? You introduce me to 5 people at the party, I hit it off with 2 of them. That's your precision. Recall is the other side of it. Of everyone at the party that I would have clicked with, how many did you actually introduce me to? Maybe there were 10 great matches in the room, and you only found 2 of them. Fine precision, lousy recall. And you can ace one while bombing the other. A recommender that shows you exactly one song, your all-time favorite, has perfect precision and basically zero recall. One that dumps the entire catalog on you has perfect recall, everything's in there, and absolutely garbage precision. The art is the balance. Someone from Amazon was once joking that eventually the goal of the recommender would be that you visit the home page, it has precisely one product on it, and you buy that product immediately. And the absurdity of that idea highlights the absurdity of having just one simple measurement. Oh, there's one more thing that this dinner party analogy misses. Order matters. On a ranked list, being right in the wrong spot barely counts. The perfect movie buried at number 40 might as well not have been there. Pretty much all of machine learning requires one key idea that can come in multiple forms: feedback. But in recommenders, most of your feedback is a shrug. You didn't click. You just scrolled past. Does that mean you hated it? A non-click is not a no, but the system has to guess anyway. There's also no real ground truth available. In recommendation, the right answer is different for every person, and it changes by the hour. Here's Ashmi Banerjee, a PhD student at the Technical University of Munich, working on sustainable travel recommendations.
So for that, we thought of generating our queries. And while looking into that, we realized another problem of this setup is that there's no single ground truth in recommendation systems or recommender systems. You can generate a bunch of data which may work factually for you, but may not work for the other person because everything has to be personalized. And this was very difficult because this is not a math problem that you have a gold standard answer and no matter what you do, you're always going to get the correct answer. This is not going to work for recommended systems. So the evaluation also needs to change, or how we evaluate the whole system needs to change.
And the thing we actually want, the little spark when a recommendation is just right, we can't measure that at all. We measure clicks and dwell time and pray they point to the real thing. Here's Corey Zeckman, a content curator at Sling TV, and one of the few industry voices I was lucky enough to talk to this season.
I think the surprise is the hard part, is that you can delight people with things that they've already known but aren't necessarily thinking about. It's that surprise part. It's hard to mathematically gauge because you can't look at whatever emotions someone's feeling. And it would be very easy to gauge if you had all the metrics on people, if you could just really gauge how happy they were, their cortisol levels, their heart rate, that kind of thing. If you could do that, I think that's when you could really measure the surprise and delight. But right now, it is more off these implicit and explicit data that, again, is just very proxy data. It's very far away from what people actually want.
Which brings us right back to that drawer at Netflix. The score you compute offline in the lab on old data. It's not the score you get from real humans in the wild. They disagree constantly. A model can win the benchmark and lose the instant it meets a person. Here's Andrea Ayana, a researcher at the University of Mannheim who studies news recommendations and filter bubbles.
By keeping all these parts fixed and then just varying, for example, we keep the news encoder fixed and vary the different user encoder approaches that we've seen out there. We saw that, okay, what really drives performance is the underlying news encoder. And again, not only in terms of ranking performance, but what we found quite surprising is also in terms of the similarity of the recommendations that they produce. So, for example, if we take list of recommendations of 10, we found out that in 70% of the cases, no matter how different the user encoders are, we have the same set of recommendations. So in practice, we maybe see a difference of 0.5 improvement in ranking, but what does this actually mean when we look at what's recommended? And what it tells us is that we don't need to invest time so much into making incrementally more complex changes, but maybe taking what's out there, understanding what really drives performance, and then using some simpler approaches.
And out in the wild, the fancy model often isn't even worth the trouble. For another industry view, here's Kunal Mukherjee, an application scientist at Zillow focused on explainable, real-time recommendations.
A surprise that I had coming from academic to industry is in industry, the preference towards a model is based on external factors rather than the internal capacity of the model. Neural network might be best suited for recommendation, but the latency of getting a prediction or the amount of data you need to keep the model updated is colossal compared to your, as you mentioned, XGBoost model or let's say histograms. So in industry, people tend to stay with simpler models more frequently rather than using some kind of a complicated model.
Now, there's a great twist in the history of recommender systems that happened in 2019, rather recently. A paper by Da Crema, Cremonesi, and Zanuck out of Politecnico di Milan with the title, Are We Really Making Much Progress? In their research, they took a pile of shiny new deep learning recommenders from the literature, the ones that had beaten all the benchmarks, and they tested them against simple, well-tuned, decades-old methods. The authors could only reproduce 7 of the 18 at all. And for those deep learning models that they couldn't seem to reproduce the good results for, they'd often lost to simple baseline things like nearest neighbor methods. Only one genuinely held up. Years of reported progress, and most of it evaporated the moment anyone ran a fair comparison. Here's Alberto Mancino, a postdoc at the Polytechnic University of Bari, and the lead author of the Data Rec Library, on how easily this can happen.
So if you deal with recommender systems in research, and in particular with offline evaluation, you will see at some point that there are flaws in this process because data sets usually are copy and paste, or authors do not refer always to the right source for retrieving these data sets, basically. And what happens is that even a smaller modification in the input can have a large impact on the output, and this can affect the performance of recommender systems and basically the comparison of the performance of different models, which is the main way we use in the research to understand if a specific approach is good or not.
And here's Florian Otzvenhofer-Baumgartner, a PhD candidate at Graz, Austria. My interview with him was about building recommenders in the digital humanities.
Just based on the nature of this domain, serendipity is very important. We're talking about research here and the context of cultural heritage. So it's about finding stuff and finding some form of identification with it. This was also reflected in the focus group interviews that I've done for this past study. And it was quite interesting because stakeholders interpreted serendipity in different ways. I've had one upstream stakeholder that was an archivist, and they argued the most beautiful finds you make are the findings that you would not expect. Okay, and then they go on, and you will rather find them by equal representation, which is quite interesting because you would rather have a notion that disentangling the system from biases would not have an effect on the serendipity.
Which forces the real question, the one hiding under all of this. If we can measure accurately, and it still isn't enough, then what are we actually optimizing for? That's the question we unpack next time on Data Skeptic. And thank you for listening to Data Skeptic, and especially to our supporters. The best way to support the show is to join Data Skeptic Plus. Visit plus.dataskeptic.com, and for $5 a month or $50 a year, you can get an ad-free version of the show. You also get access to the full version of our graphs course, or if you want to check out the first 2 chapters for free, you can sign up with no commitment at plus.dataskeptic.com. Or if you'd rather grab some merch, head over to dataskeptic.com and click on the store. I think the Graphs and Network Season t-shirt is the best item we've got, but your mileage may vary. That's my recommendation for today. My second recommendation is tune in next time for part 2 of the Recommender System finale. My third and final recommendation is to check out Run and Punch over on Spotify. They're going to take us out here with We've Never Met.